Hello, let's restudy a book called Programming Logic and Design by Joyce Farell. So, this is one of the books that I really like, and it's very helpful for a first year computer science student. I'm still in first year, but yeah, I'm kind of bored, so let's restudy this book. So, the first section or the first chapter is an overview of computers and programming. So, the very first lesson is understanding computer systems. A computer system is a combination of all the components required to process and store data using a computer. Every computer system is composed of multiple pieces of hardware and software. So, hardware is the equipment or the physical devices, for example, keyboards, mice, speakers, and printers are all hardware. The devices are manufactured differently for computers of varying sizes. For example, large mainframes, laptops, and very small devices embedded into products such as phones, cars, and thermostats. The types of operations performed by different sized computers, however, are very similar. Computer hardware needs instructions that control its operations, including how and when data items are input, how they are processed, and the form in which they are output or stored. So, for software, it is the computer instructions that tell the hardware what to do. Software is programs. Is programs? Anyways, a program is a set of computer instructions written by a programmer. So let's take a look of a program. Oh, I cannot see it. Anyways, written by a programmer. You can buy pre-written programs that are stored on a CD or DVD or that you download from the web. For example, businesses use word processing and accounting programs, and casual computers and users enjoy programs that play music and games. Alternatively, you can write your own programs. When you write software instructions, you are programming. This course focuses on developing program logic. The logic of computer program is the complete sequence of tasks that lead to a problem solution. A program's logic is similar to a story's plot. It is a series of steps that lead to a conclusion. So software can be classified into two broad types. So application software and system software. So application software are all the programs you apply to a task such as word processing programs, like Microsoft Word, spreadsheets, payroll and inventory programs and games. So the node when you hear people say they have downloaded an app, they are simply using the abbreviation of application software. So application software are basically the ones in your phone and the ones that that you usually or regularly use in a computer. So system software on the other hand is comprising the programs that you use to manage your computer, including operating systems. An operating system is software that supports a computer's basic functions, including controlling devices such as keyboard and mice and scheduling tasks. Some operating systems you might know include Windows, Linux, or Unix for larger computers, and Google Android and Apple iOS for smartphones. This course focuses on the logic used to write application software programs rather than the software programs, but many of the concepts apply to both types of software. Together, computer hardware and software accomplish three major operations in most programs. So this is very simple. Oh, we've learned this multiple times. So we have the IPO, input, processing, and output. We don't need to read all of those. Basically, input data items include all the text, numbers, data that are entered into and processed by a computer. So let's so hardware devices perform input operations include keyboards and mice, Um, uh, it can also include items such as images, sounds, and a user's mouse or fingers swiping movements. Next is processing or the process. This is the working or this is the actual work from our input or from our data. So it means working with them, for example, organizing or sorting, checking for accuracy, performing calculations. So the hardware component that performs these types of tasks is the central processing unit or the CPU or the how do you call this? It is the brain of the computer. So some devices such as tablets and smartphones usually contain multiple processors, including those that specialize in processing graphics. Efficiently using several CPUs require special programming techniques. Next is output. Programming professionals often use the term data for input items, but they use the term information for data items that have been processed and output. So, the resulting information is sent to a printer, monitor, or some other output device so people can view and interpret and use the results. So, sometimes you place output on a storage device such as hard drive, flash media, or a cloud-based device. So the cloud refers to devices at remote locations accessed through the internet. So like iCloud, probably Microsoft Drive, and yeah, people cannot read or interpret data directly from these storage devices, but the devices hold information for later retrieval. Okay, moving on. You write computer instructions in a computer programming language such as Visual Basic, C Sharp, C++, or Java. Just as some people speak English and others speak Japanese, programmers write programs in different languages. Some programmers work exclusively in one language rather, whereas others know several and use the one that is best suited to the task at hand. If I'm not mistaken, Minecraft is built with Java, and and I've heard or I've read somewhere that Java is not really a good programming language to build games, but somehow the creator of Minecraft managed to execute a Minecraft in Java, and now it is, if not the most popular game. So just a fun fact that I don't know if it's fully true, but yeah, I've heard it somewhere before. So the set of instructions you write using a programming language is called program code. When you write instructions, you are coding the program. Every programming language has rules governing its word usage and punctuation. These rules are called the language's syntax. Mistakes in a language's usage are syntax error. If you ask how to get to store do I, in English, most people can figure out what you probably mean, even though you have not used proper English syntax. You have mixed up the word order, misspelled a word, and used an incorrect word. However, computers are not nearly as smart as most people. In this case, you might as well have asked the computer this type of sentence, unless the syntax is perfect. The computer cannot interpret the programming language instructions at all. So I think this just basically say computers will never be in the same level as humans because of the complexity and understanding. You know, as it says that a human can understand a bit of error, but still can translate it to the actual message, but computers on the other hand cannot because they only understand the word as is or the actual syntax. When we mean syntax, we mean the rules that govern a specific programming language. So yeah, when we input syntax, we must be sure that it is completely correct. Otherwise, it will produce syntax errors or the mistakes in a programming language. So this is just a table, example table, that shows how you can use several common programming languages to write a statement that displays the word hello on a single line on a computer monitor. Okay, so this is it in different programming languages that displays hello on a single line. Okay, moving on. When you write a program, you usually type its instructions using a keyboard. When you type program instructions, they are stored in a computer memory, which is a computer's temporary internal storage. So RAM or random access memory is a form of internal volatile memory. Programs that are running and data items that are being stored in RAM are for quick access. So internal storage is volatile. Its contents are lost when the computer is turned off or loses power. Usually, you want to be able to retrieve and perhaps modify the stored instructions later, so you also store them on a permanent storage device such as a disk. Permanent storage devices are non-volatile, that is, their contents are persistent and are retained even when power is lost. If you have had a power loss while working on a computer, but were able to recover your work when a power was restored, it's not because the work was still in the RAM or the random access memory. It's because your system was configured to automatically save your work at regular intervals at a non-volatile storage device, often your hand, often your hard drive or a remote drive on the web. So remember, random access memory or RAM is the volatile memory that stores temporary data. When you um, so permanent storage devices are non-volatile, meaning it is persistent and it's not temporary. It stores data even after you turn off a computer. After a computer program is typed using programming language statements, it's stored in memory. It must be translated to machine language that represents the millions of on and off circuits within the computer. These are the ones and zeros. So your programming language statements are called source code, and the translated machine language statements are object code. We have okay again, programming languages are called source code. The translated machine language are the object code. So each programming language uses a piece of software called a compiler or an interpreter to translate your source code into a machine language. Okay, we're gonna differentiate compiler and interpreter. I think in the upcoming lessons. But anyways, machine language is also called binary language because it can only understand ones and zeros, right? So and it's represented as a series of zeros and ones. The compiler or interpreter that translates your code tells you if any programming language component has been used incorrectly. Syntax errors are relatively easy to locate and correct because your compiler or interpreter highlights them. So note, although there are differences in how compilers and interpreters work, the basic function is the same: to translate your program statements into code the computer can use. When you use a compiler and the entire and this is the difference. A compiler When you use a compiler, the entire program is translated before it can execute. While on the other hand, an interpreter, when each instruction is translated just prior to the execution. So that's the difference. So a compiler, the entire program, keyword, entire program. Interpreter, each instruction is translated line by line. So usually you do not choose which type of translation to use. It depends on the programming language. However, some languages can use both compilers and interpreters. After a program source code is translated successfully to a machine language, the computer can carry out the program instructions. When instructions are carried out, a program runs or executes. In a typical program, some input will be accepted, some processing will occur, and results will be output. Okay. 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 So, two truths and a lie. This is a mini quiz for this lesson. Hardware is the equipment or the devices associated with a computer. Software is the computer instructions. That is true, right? The grammar rules of a computer programming language are its syntax. Correct. You write program using machine language and translation. Software converts statements into a programming language. This is the lie because you write programs using programming language and translation software converts the statements to a machine language. So we should swap machine language and programming language. Programming language first, then it's gonna be translated to a machine language because a computer can only understand series of zeros and ones. Okay, so the false statement is third one. Okay, so we have this next lesson. Understanding simple program logic. For a program to work properly, you must develop correct logic. That is, you must write program instruction in a specific sequence. You must not leave out any instructions and you must not add extraneous instructions. For a program with syntax errors cannot be translated fully and cannot execute. A program with no syntax errors is translatable and can execute, but it might still contain logical errors and produce incorrect output as a result. Suppose you instruct someone to make a cake as follows. So get a bowl. So you're instructing someone, right? Get a bowl, stir, add 2 eggs, add a gallon of gasoline, bake at 350 degrees for 45 minutes, add 3 cups of flour. This is basically, if you see this, there's no syntax errors because in English it's understandable, right? But we have logical errors. Why is that? Because get a bowl, stir, add 2 eggs, then add a gallon of gasoline. It just logically it doesn't make sense because why would you add gasoline, right? So the don't do it icon points to the line number 4 because you should not bake a cake like that. That's basically it. So logical error, it can have a correct syntax, but when you think about it logically, it's not correct. So that can be applied in analyzing code. you could have the perfect syntax, but if you cannot write based on the given instructions, then your code isn't efficient, or it's still wrong even though it has a correct syntax. So even though the baking instructions are use English language syntax correctly, it is out of sequence. So if you follow this instruction, you will not make a edible cake. You may end up with a disaster. Many logical errors are more difficult to locate than syntax errors. It is easy for you to spell eggs in a recipe than it is for you to tell if there are too many eggs or if they are added soon. Many simple computer programs include steps that perform input processing and output. Suppose you want to write a computer program to double any number you provide. You can write the program in a programming language such as Visual Basic or Java, but if you were to write it using English like statements, it would look like this. So, we need to familiarize ourselves with this um, types of things because we're gonna encounter a lot of this, of a lot of pseudocodes. But before that, we just need to analyze the logic of the given examples here. So that is a program that doubles any number that is provided. Next. Okay, let's analyze this. That's what the books want us to do. So doubling number process includes three instructions. Okay, so the first one, the instruction to input my number. The very first one is an example of an input operation. When the computer interprets this instruction, it knows to look to an input device to obtain a number. When you work in a specific programming language, you write instructions that tell the computer which device to access for input. For example, when a user enters a device as data for a program, the user might click on the number with a mouse, type it from a keyboard, or speak it into a microphone. Logically, however, it doesn't matter which hardware device is used as long as the computer knows how to accept a number. When a number is retrieved from an input device, it is placed in the computer's memory in a variable named my number. So, in a variable named my number. So, a variable is a named memory location whose value can vary, that is hold different values at different points in time. For example, the value of my number might be 3 when the program is used for the first time and 45 when it is used the next time. In this course, as well as in most or almost all programming languages, variable names will not contain embedded spaces. For example, a variable name might be my number instead of my number. I think we will be learning syntax for naming variables in the future lessons here in this book. Okay, so a college classroom is similar to a named variable in that its name, for example, 204 Adams Building, can hold different contents at different times. For example, your logic class might meet there on Monday night and a math class might meet there on Tuesday morning. So the instruction my answer is equals my number times 2 is an example of processing operation. In most programming languages, an asterisk is used to indicate multiplication, so this instruction means change the value of memory location, my answer, to equal the value at the memory location my number times 2. So mathematical operations are not the only kind of processing operations, but they are very typical. As with input operations, the type of hardware used for processing is irrelevant. After you write a program, it can be used on on computers of different brand name sizes and speeds. So in the number doubling program, the output my answer instruction is an example of an output operation. Within a particular program, the statements could cause the output to appear on the monitor, which might be a flat panel, plasma TV, or smartphone display. The output could go to a printer, which could be a laser or inkjet. The output could be written to a disk or DVD, or the output could be spoken words sent to a headphones. The logic of the output process the same no matter what hardware device you use. So when the instruction executes, the value stored in memory at the location in my answer is sent to an output device. So the output value also remains in the computer memory until something else is stored at the same memory location or power is lost. Basic input output. Okay, I don't think we should do this. Anyways, I think that's all for this part. It's all about the input, process, and output, correct use of syntax, applying input, process, output to a to logic and the sequence of a pseudocode, then analyzing which part is the input, output, and process, variables, what else? Basically, that's it for this section. So let's answer this through two truths and a lie. So a program with syntax errors can execute but might produce incorrect results. A program with can execute. This is the lie because a program cannot execute with syntax errors. You know. So this is true because it's two truths and a lie. So basically, two and three are truths. Although the syntax of programming languages differs, the same program logic can be expressed in different languages. That is true. Most simple computer programs include steps that perform input, processing, output. Okay, so number one is the lie. Okay, next. Okay, so we have the program development cycle. A programmer's job involves writing instructions such as those in the doubling program in the preceding section, but a professional programmer usually does not just sit down at a computer keyboard and start typing. We have the program development cycle, in which can be broken down into 7 steps at least. So, first, understand the problem. Second is plan the logic. Code the program for 3. Fourth one is use software, a compiler, and interpreter to translate the program into machine language. You test the program, put the program into production, and maintain the program. So this is the diagram. It's very important to be familiar with this. Understand, plan, write, translate, test, put into production, and maintain. Then maintaining, if we discovered any anomalies or any errors, and understand the problem again, then that's why it's called a cycle. So a diagram depicting the stages of program development cycle listed in a circle, understand the problem, and to maintaining the program. This is the program development cycle. Okay. First one, understanding the problem. Professional computer programmers write programs to satisfy the needs of others, are called users or end users. Examples of end users include human resources department that needs a printed list of all employees, a billing department that wants a list of clients who are 30 or more days overdue on their payments, and an order department that needs a website to provide buyers with an online shopping cart. Because programmers are providing a service to these users, programmers must first understand what the users want. When a program runs, you usually think of the logic as a cycle of input, processing, output operations. But when you plan a program, you think of the output first. After you understand what the desired result is, you can plan the input and processing steps to achieve it. So suppose the director of human resources says to a programmer, our department needs a list of all employees who have been here over 5 years because you want to invite them to a special thank you dinner. On the surface, this seems like a simple request. An experienced programmer, however, will know that the request is incomplete. For example, you might not know the answers to the following questions about which employees to include. Does the director want a list of full-time employees only, or a list of full and part-time employees together? Or does the director want to include the people who have worked for the company on a month-to-month contractual basis, or over the past 5 years, or only regular permanent employees? Do the listed employees need to have worked for the organization for 5 years as of today, and such that? So basically, the essence of this is it lacks the specific information about which employees to invite the special thank you dinner. The programmer cannot make any of these decisions. The user or the human resources director must address these questions. More decisions still might be required. For example, what data should be included for each listed employee? Like, should they contain the first and last names, social security numbers, phone numbers, addresses, etc.? Should the list be in alphabetical order, employee ID, order, etc.? Should the employees be grouped by any criteria, such as department numbers or years of service? So, several pieces of documentation are often provided to help the programmer understand the problem. So, documentation in keyword documentation consists of all the supporting paperwork for a program. It might include items such as original requests for the program from users, sample output, and descriptions of the data items available for input. Understanding the problem might be even more difficult if you are writing an app that you hope to market for mobile devices. Business developers usually are approached by a user with a need, but successful developers of mobile apps often try to identify needs that users aren't even aware of yet. For example, no one knew they wanted to play specific online games or post photos to social media before such applications were developed. Mobile app developers are also must consider a wider range or variety of user skills than programmers who develop applications that are used internally in a corporation. Mobile app developers must make sure their programs work with a range of screen sizes and hardware specifications because software competition is intense and hardware changes quickly. Fully understanding the problem may be one of the most difficult aspects of programming. On any job, the description of what the user needs may be vague. Worse yet, users may not really know what they want. And users frequently change who think they know frequently change their minds after seeing sample output. A good programmer is often part counselor, part detective. I think this is pretty understandable. this part of understanding the problem. So the next part of the program development cycle is, wait, no, planning the logic. So the heart of the programming process lies in planning the program's logic. During this phase of the process, the programmer plans the steps of the program, deciding what steps to include and how to order them. You can plan the solution to a problem in many ways. Two common planning tools are flowcharts and pseudocode. So this is the heart of basically what I've learned in that this course when we in back in first term. So flowcharts and pseudocodes are very important. So you will learn more about these tools later. And both tools involve writing the steps, program in English. You could actually choose just one, but I prefer what I prefer flowcharts because it uses shapes, easier to navigate if ever. It's like a tree branch, and it is more visually captivating float than pseudocode, which basically like a code but it's written in pure English. So you may hear programmers refer to planning as a program as developing an algorithm. So an algorithm is a sequence of steps or rules you follow to solve a problem. The programmer shouldn't worry about the syntax of any particular language during the planning stage, but should focus on figuring out what sequence of events will lead to will lead from the available input to the desired output. So planning program's logic includes thinking carefully about all the possible data values a program might encounter and how you want the program to handle each scenario. The process of walking through a program's logic on a paper before you actually write the program is called desk checking. So it is the process of walking through a program's logic on a paper before you actually write it. So you will learn more about planning the logic throughout this course. And like in fact the course focuses on this crucial step almost exclusively. Third one, third out of seven, coding the program. So the programmer can write the source code for a program only after the logic is developed. Hundreds of programming languages are available. Programmers choose particular languages because some have built-in capabilities that make them more efficient than others at handling certain types of operations. Despite their differences, programming languages are quite alike in their basic capabilities. Each can handle input operations, arithmetic processing, output operations, and other standard functions. The logic developed to solve a programming problem can be executed using any number of languages. Only after choosing a language must the programmer must be concerned with proper punctuation and correct spelling of commands. In other words, using the correct syntax. An experienced programmer can successfully combine logic and planning and program coding in one step. This may work for planning and writing a very simple program, just as you can plan and write a postcard to a friend using one step. A good term paper or Hollywood, however, needs planning before writing, and so do most programs. Which step is harder, planning the logic or coding the program? Right now, it seems to you that writing in a programming language is a very difficult task, considering all the spelling and syntax rules you must learn. But however, that is more on memorization, so the planning step is actually more difficult. Which is more difficult, thinking up twists and turns to the plot of best-selling mystery novel or writing a translation of an existing novel from English to Spanish. And who do you think gets paid more, the writer who creates the plot or the translator? So that's a good analogy. Planning basically, you create an algorithm Coding is just translating it to a programming language. So, note in some organizations, system analysis programmers and coders have slightly different jobs. An analyst might talk with users to determine their needs. A programmer might design the logical steps in a program, and a coder might then write the designed instructions in a programming language. However, there is overlap in these jobs, and one employee might fill all of these three roles in some organization. Okay, so to recap, we have understanding the problem, planning, planning the logic, and coding the program. Fourth one, using software to translate the program into machine language. So even though there are many programming languages, each computer works internally with one language, and it's machine language, consisting of zeros and ones. Computers understand machine language because they are made of thousands of tiny electrical switches, each of which can be set either on the on state or the off state, which are represented by a 1 or 0 respectively. So languages such as Java or Visual Basic are available for programmers because someone has written a translator or a program or a compiler or an interpreter that changes the programmer's English like high level programming language into machine language that the computer understands. Machine language is an example of low level programming language. Some other languages not far removed from machine language are also referred to as low level languages. When you learn the syntax of a programming language, the commands work on any machine on which the language software has been installed. Your commands, however, then translated to machine language, which differs in various computer makes and models. So if you write a programming statement incorrectly, like misspelling, the translator program doesn't know how to proceed and issues an error message identifying the syntax error. Although making errors is never desirable, syntax errors are not a programmer's deepest concern because the compiler or interpreter catches every syntax error and displays a message about the problem. The computer will not execute a program that contains even one syntax error. So that's why our answer earlier is wrong in the two truths and one lie. So typically a programmer develops logic, writes the code, and compiles program, receiving a list of syntax errors. The programmer then corrects syntax errors and compiles the program again. Correcting the first set of errors frequently reveals new errors that originally were not apparent to the compiler. For example, if you could use an English compiler and submit the sentence, the DG chased the cat. The compiler might first point out only one syntax errors. The second word DG is illegal because it is not part of the English language. Only after you corrected the word to dog would the compiler find another syntax error on the third word chase because it is wrong verb form for the subject dog. This doesn't mean chase is necessarily the wrong word. Maybe dog is wrong. Perhaps the subject should be dogs. In which ca- in which in which case chase is right. Compilers don't always know exactly what you mean, nor do they know what the proper correction should be. But they do know when something is wrong with your syntax. Programmers often compile their codes one section at a time. It is far less overwhelming and easier to understand errors that are discovered in 20 lines of code at a time than to to correct mistakes after 2000 lines of code have been written. When writing a programmer might need to recompile the code several times. An executable program is created only when the code is free of syntax errors. After a program has been translated into machine language, the machine language program is saved and can be run any number of times without repeating the translation step. You need to retranslate your code only if you make changes to your source code statements. So this is figure 1.201-2. So write and correct the program code, compile. There are syntax errors, you will rewrite them. If there are no syntax errors, proceed to execute. So, and produce an output. Okay, let's just move on to testing the program. A program is free of syntax. Sorry. A program is free of syntax is not necessarily free of logical errors. A logical errors a logical error results when you use a syntactically correct statement but use the wrong one for the current context. For example, the English sentence, the dog chases the cat, although syntactically perfect, is not logically correct if the dog chases a ball or the cat is the aggressor. After a program is free of syntax errors, the programmer can test it. That is, execute it with some sample data to see whether the results are logically correct. Recall the number doubling program earlier. So, if you execute the program, provided that the value 2 as the input to the program and the answer 4 is displayed, you have executed one successful test run for the program. However, if the answer 40 is displayed, maybe the program contained logical error, maybe the second line code was mistyped with an extra zero so that the program reads as my number times 20 instead of 2. So placing 20 instead of 2 in the multiplication statement caused a logical error. Noticing that Notice that nothing is syntactically wrong with this second program. It is just as reasonable as multiplying with 2. But if the programmer intends only to double, then logical error has occurred. So the process of finding and correcting program errors is called debugging. You debug a program by testing it using many sets, then enter 2 and get the output value of 4. That doesn't necessarily mean you have a correct program. Perhaps you have typed this program by mistake because you inputted a plus sign instead of an asterisk or multiplication. So an output or an input rather of 2 results in an answer of 4, but that doesn't mean your program doubles number. It actually adds 2 to them. If you test your program with additional data and gets the wrong answer, for example 7, and the output is 9, you know there's a problem with your code. Selecting test data is somewhat an art itself, and it should be done carefully. The Human Resources Department wants a list of names of 5-year employees. It would be a mistake to test the program with a small sample file of only long-term employees if no newer employees are part of the data being used for testing. You do not really know if the program would have eliminated them from the 5-year list. Many companies do not know that their software has a problem until an unusual circumstance occurs. For example, the first time an employee has more than 9 dependents, the first time customer orders more than 999 items at a time, or when the internet runs out of allocated IP addresses, a problem known as IPv4 exhaustion. I'm also not familiar with that. But anyways, I think the essence of this is that logical errors are just as important as syntax errors because the intended by a request or from the user from the end user must be accomplished because that's the goal, right? So with logical errors, it's very important to analyze it in your code because as you can see here, if you don't have a good set of data or you don't debug it properly, you can have a correct answer. For example, this 2, it looks like it is a correct answer, logically same as 2 times 2, but what we need is more sample data, because if you just add 2, for example, to a given inputted number 7, which is gonna cost 9. So it's very important to be familiar or to know exactly what the program wants or what the program is intended for, so that we could, you know, reduce or eliminate logical errors. I think this is second to the last, if I'm not mistaken. Putting the program into production. After the program is thoroughly tested and debugged, it is ready for the organization to use. Putting the program into production might mean simply running the program once if it was written to satisfy a user's request for a special list. However, the process might take months if the program will run on a regular basis, or if it is one of a large system of programs being developed. Perhaps data entry people must be trained to prepare for the input for the new program. Users must be trained to understand the output, or existing data in the company must be changed to an entirely new format to accommodate the program. Keyword conversion, or the entire set of actions an organization must take to switch over to use a new program or set of programs can sometimes take months or years to accomplish. Keyword for this step is conversion. So, switching over to a new program or set of programs. So, that's it for this step, putting the program into production. Another keyword is test. No, no. After that, um, people train to understand data, new format, adapt also. So that's it. Next, I think this is the last. Maintaining the program. This is the seventh part of the development cycle. So after programs are put into production, making necessary changes is called maintenance. Maintenance can be required for many reasons. As examples, new tax rates are legislated, format of an input file is altered, or the end user requires additional information not included in the original output specifications. Frequently, your first programming job will require maintaining previously written programs. When you maintain the programs others have written, you will appreciate the effort the original programmer put into writing clear code, using reasonable variable names, and documenting his or her work. When you make changes to existing program, you repeat the development cycle. That is, you understand the changes, the plan, code, translate, and test them before putting them into production. If a substantial number of program changes are required, the original program might be retired, and the program development cycle might be started for a new program. So this is the end point of the program development cycle, but it could be um, another tunnel for another kind of program development cycle if we want to change a program entirely, or if we want to make a change minimal, or somewhat a big chunk of change, then we still must go on to the program development cycle. So let's answer these two truths and a lie, since we already discussed the seven parts or 7 steps of program development cycle. So to recap, we have the understanding the problem, planning the logic, that's the coding the coding the program, um, translating the program into machine language, testing the program, putting program into production, maintaining the program. So again, maintain. So again, the first one is understanding the problem, planning the logic, coding the program, translating it to machine language. What's the fifth one again? Translating it to machine language. What's the fifth one? Wait. Sorry, this is my fault. Testing. Okay. Okay, translating, testing. So testing the program. Next is putting the program into production, and lastly is maintenance. So again, understanding the problem, planning the logic, coding the program, translating it to machine language, testing the program, putting it in production, and maintenance. Okay, let's answer these 2 truths and a lie for the understanding the program development cycle. Understanding the problem that must be solved can be one of the most difficult aspects of programming. That's true. The two commonly used logic planning tools are flowcharts and pseudocodes. That's true. Developing program logic is a very different process when you use different programming languages to implement the logic. That is not true, that is the lie, because although different programming languages have different syntax, the development program logic are kind of similar because you're just developing the algorithm, or you're just developing the actual logic for the system that you want to develop. So let's check the answer. Yes, it's number 3. The explanation is despite their differences, it is similar in their basic capabilities. It can handle input, processing, and output operations and other standard functions. The logic developed to solve a programming problem can be executed using a number of languages. So, in this video, I think we discussed um, 3 lessons. So, we discussed the understanding computer systems. We learned about hardware, software, types of softwares, the IPO, basic terminologies or the keywords to note. Then we also discuss understanding simple program logic. This is basically an example of a of a simple IPO in expression of a pseudocode where we can identify logical errors. Then and identifying the IPO. Then lastly, for this video, we discussed about understanding the program development cycle. So these are the 7 steps for the program development cycle. So next, I think we're gonna discuss about pseudocode statements and flowchart symbols. So this is the next. So probably we're gonna discuss that as well as 1.5 and excuse me. 1.5 as well, using a sentinel value to end a program, to 1.6, as well as 1.7, since that's the last topic for chapter 1, an overview of computers and programming. So I think we've learned a lot today. So yes, I think that's it for today. And let's restudy this book by Joyce Farell for the next video for this book. So yes, I really like this book. I think it's a good introduction, especially when you don't know that much when it comes to programming languages. Because I think you should not start, learning right away the Python, C Sharp, C++. You must start with the basics of logic. And I think this is a good book for that. The structures, sequences, before it is translated into the actual programming languages, in which they only differ on syntax. So yes, this is our book. So that's all.